recording. We appreciate it if people on Zoom are muted, people in the room are not broadcasting with their phones. Dr. Bob Bolton is our speaker for today. He's Deputy of Operations for the NGEE Arctic program at ORNL. That's NG stands for Next Generation Ecosystem Experiments in the Arctic. Bob has an interesting history. He's a Westerner. He's probably just still getting used to living in Tennessee. It's completely different from his background. He grew up, most of his youth was spent in Wyoming and a little bit in Idaho. At some point, his family moved to Alaska, so he became an Alaskan. He did go to college in California at the California Lutheran University. Got a bachelor's degree in geology, which I can relate to as another geologist. Master's of Science degree later in geologic engineering from the University of Alaska Fairbanks, and a PhD in hydrologic engineering from the University of Alaska at Fairbanks. So he comes from a strong Western background. And now as Deputy Director of Operations for the NGEE Arctic project, he's responsible for safety, community engagement, outreach, international collaborations for that project. He's obviously well qualified for that because he spent 12 years as a research assistant associate professor in the International Arctic Research Center at the University of Alaska. So knowing how complicated life can be in Alaska, if you've ever visited there or worked there, you recognize that. I think he's well qualified to do that operations job. But his personal research has focused primarily not on operations, but rather on understanding the magnitude, timing, and pathways of water fluxes in permafrost affected environments, with an emphasis on vegetation and snow and permafrost interactions. And permafrost is an interesting topic in the life of recent climate change. So I think he'll have some interesting stories to tell us about permafrost and his work there. So no further ado, Dr. Bob Bolton.
Okay. So I need to share again. This comes up again. Yeah, thank you for the introduction and get going here as soon as I see my screen. Okay, there we go. Thank you. So thank you all for coming out and braving the rain. It's a bigger crowd than I was expecting given the amount of rain. And maybe not so much rain for you all, but it's pretty wet for this time of year. So today I'm going to talk to you about my research and a little bit about Alaska and a little bit about permafrost and the research I've been doing and a little bit of outreach that I've been doing. At the end of the talk, I planned to play an audio clip, but I was not able to get the sound to work. And so we'll skip through that, but if those people that want to stick around and listen to the podcast, then I'll play that separately on a speaker and we'll turn off the Zoom and hopefully avoid the feedback. But it's a pretty cool audio experiment or audio clip. And so my talk is going to be basically 3 different parts. So it'll be a fairly long introduction and background section, talk about permafrost, what it is, what it means, how it impacts the environment. I'll speak a little bit about my permafrost related research. And then at the end, I'll speak about the podcast and outreach program. So an introduction to myself, and Alan, thank you for the introduction. Again, I come to you after being in Alaska for over 35 years. My parents moved up there when I was a junior in high school. And so it was a pretty big change going from a little tiny town of 2,000 to what I thought was a big city in Fairbanks, Alaska, which I've learned since is not. And from there, I went to college, came back for grad school, went away for a postdoc, and then came back again and was a professor at the university, a research professor since 2009. So all of my research, 99.9% of it has focused on the Arctic and subarctic processes. And like I was introduced, I just moved down here this past July. About 14 or 15 months ago, Colleen Iverson, who's sitting in the back, and Stan Walschlager, who I believe is online, approached me and said, "Hey, do you want to come to Tennessee?" And it was a new and exciting opportunity, new and different position and responsibilities, being on a bigger team. And we took advantage of that. And so my wife and I, Rachel, who's showing down there in the bottom left, we packed up the good and the bad, including the 22 hours of daylight in the summertime and the 4 hours of daylight in the wintertime, the aurora. Packed up our trailer and we drove 2 weeks and exactly 5,130 miles, 0.0 from. But we didn't all come together. We lost a trailer on the way down in Montana. But that's a whole different story, but it was quite an experience for both of us. And so I started at Oak Ridge National Lab in 2023 in July, so about 9-ish months ago, I guess now. And I am the Deputy of Operations for the BER sponsored Next Generation Ecosystems Experiment in the Arctic. And so just a little bit about what the NGEE Arctic project is. The overall goal of the NGEE Arctic project is to better represent Arctic processes in the DOE's climate model. So advancing the processes and our understanding of the tundra processes in the model. This has been a long-term project. We started in 2012 and it's ongoing. We're just about ready to wrap up our phase 3 and we're leaving our field work in Alaska at the end of this summer. And we just found out last week that our phase 4 proposal was accepted by DOE, and we'll begin that on October 1st, and that will continue for another 3 years beyond that. And with our phase 4, we'll be taking what we've learned in Alaska, and applying that to the Pan-Arctic through modeling studies. And so the NGEE Arctic project is a pretty cool experiment. It includes having field observations that are informed by modeling questions. We spend a lot of time on the ground, done a ton of field work in both Utqiagvik, Alaska, which is the northernmost point. It was formerly the city of Barrow, the town of Barrow, and then also on the Seward Peninsula, based out of Nome, which is far west in Alaska. And these are two different continuums where Utqiagvik is very cold, very deep permafrost, and the other end on the Seward Peninsula is very warm permafrost, relatively warm permafrost, and discontinuous permafrost. So we're spanning a gradient of permafrost conditions. Our field work and our field studies have informed how we do our modeling, and we started out at different scales. Our field measurements inform very fine scale measurements, shown here on bottom left, and then we start scaling up, we scale up, and we scale up. And for phase 4, we'll be applying our model across the Pan-Arctic. In the NGEE Arctic project, we ask questions that span permafrost thaw to shrub expansion to distribution of water across the landscape. And we quantify the drivers and understanding of those processes. The NGEE Arctic project is organized around 6 basic science questions spanning landscape. So Q1 is landscape, so permafrost and how permafrost evolves and degrades over time and the interactions. So the landscape processes. The question 2 is the biogeochemistry. How do the microbes in the soil interact and release carbon in its different forms? The Q3 is better understanding and quantifying the plant traits that were not included in the original climate model when the project started. The 4th question involves interactions of shrubs and shrubs encroaching on the northern landscape. And the interactions with permafrost and water and such. The Q5 question is the question that I've been most involved with. This hydrology question is meant to be an integrating question of the Q1 through 4 as well as 5. That deals with how water is on the landscape, how it moves through the landscape, under the landscape, and how it's distributed. And then in phase 3, we introduced a 6th question, which is disturbance. And we're looking at how wildfire and thermal karst, which is the degradation of permafrost and the change in landforms due to changing permafrost, how that is that weed, how that interacts. And so how does disturbance impact all these different processes? So we have a different gradients of topography, permafrost vegetation, and hydrology across our questions. So here are just some photos of the landscapes that we work in. The top 2 photos are Ukhiavik, Alaska, very flat. It's not my favorite place, it's probably it's very flat, low center polygons, different types of polygons, polygonal tundra. And then the bottom series of photos and the top right are different places that we work in Alaska. We're on the Seward Peninsula. We have 3 different primary field sites, including pretty flat down here on the bottom left. That might actually be or but we have more topography. We have shrubs, bigger topography landscapes. We have and shrubs on the Seward Peninsula. So very different environments and topography.
What is the long walkway on the middle picture?
And so that goes out to the shed, the control shed. And so the permafrost is quite sensitive to walking and disturbance of any kind. And so we walk on boardwalk to avoid degrading the permafrost. And on a later slide, I'll show a picture of a thermal erosion. So where I wasn't taken care of, and I caused a big, basically gully across the landscape because the permafrost was too warm and I disturbed the permafrost. And so we use that to protect the permafrost primarily. Yeah, feel free to answer or ask questions as you wish. So why do we care about this? Here is a plot showing the red is the Arctic air surface temperature, and blue is the global surface temperature. 2 different products. One is based on measurements, and the Era 5 is based on reanalysis. But over time, and more in the currently, you see that the red line is increasing at a rate that's about 3 to 4 times the rate of the global average. And so quite rapidly. And this change is continuing on into the future. So these are recent so anomalies from 1991 compared to the 1991 to 2020 average. The surface temperature for the whole Arctic, including the ocean, and only the land part going forward. So how different is the temperature? And you see around 2005-ish that the temperature started to increase, and they haven't really slowed down in terms of the global or the long-term average. It goes up and down, but it's definitely increasing. If we look closer to just Alaska, this is a plot from the Alaska Center for Climate Assessment and Policy. What's going on there? And so this is showing statewide temperatures, so everywhere from Juneau all the way to Nome up to Boreal, Ukhiavik. And this is showing the annual temperature with a smoothed average over time. The blue dots on this show the 10 coldest years on record from 1900 to 2023. And the red dots show the top 10 warmest years on record. And you can see that 2023 hits the long-term smoothed average. So it's kind of an average year in the smoothing, but if you look across, it's almost higher than every year prior to, you know, yeah, 2000. And so last year, even though it's now the average temperature, smoothed average, it's still warmer from everything the 20 years ago. So quite a big change. And here's another plot that sort of puts that in perspective as well. So this is the same data set from 1900 to 2023. These are called climate stripes. And so basically we've ranked every year and placed a value on it. So the coldest year is the darkest blue. The warmest temperature on record is the brightest red, with the white temperatures or the neutral colors close to the long-term average. So this is basically the ranking, and what you see is that on the far left was a lot colder, and as we move forward into the future, it's a lot warmer. It's almost always red. 2021 was a bit of a down year, a little bit cooler, a little bit closer to average for Alaska, but it was warmer in other places in the Arctic. So let's talk a little bit about permafrost. This is what I do. I'm a permafrost person. And so permafrost, so I'll just define what it is. It's any ground that remains frozen for 2 or more consecutive years. It can be any combination of soils or rocks or ice. It formed about 10,000 to 100,000 to 10,000 years ago during the last ice age. And it composes about 24% of the land area in the northern hemisphere. So it takes up a huge amount of land. The other interesting part about it is it stores, because it's so cold, it's frozen, and things degrade and move a lot slower. There's a huge buildup of carbon in the soils. And in permafrost regions in the northern hemisphere, there's about 2.5 times as much carbon stored in the ground than is actually in the atmosphere right now. And so there's a bit of fear that if this carbon is released into the atmosphere, then the cycle continues in a positive way in terms of warming. There are different types of permafrost. You can see hopefully the different color shadings. There's continuous permafrost, which encompasses the far northern latitudes. This is very cold permafrost. It's very deep permafrost. It can be many hundreds of meters deep, and it can be very, very cold, very stable permafrost. And then as you move southward into interior Alaska, it turns into a lighter shade blue. This is discontinuous permafrost. And so this is permafrost that covers 50% to 90% of the landscape. And so in interior Alaska, this is typically south-facing slopes where the sun doesn't hit, because the sun's always in the south. So if you have a south-facing slope, it's always shaded or primarily shaded and less energy. So that area is typically permafrost. Then on south-facing slopes where the sun angle is slow but hits it directly, the landscape directly, then that tends to be permafrost free. And this permafrost is quite warm, often very close to 0 degrees Celsius or 32 degrees Fahrenheit. And this permafrost can be in the tens of feet. I'm mixing my units, and so I apologize. But this is very shallow permafrost, very unstable permafrost. And the difference between the two, I like to think of as sort of like ice cream. And so if you have half a gallon of ice cream and you put it in the deep freezer, and you take it out and you try to scoop it out, it's really hard to dig in, right? It's really stable. But if you let the ice cream warm up a bit, and it gets to the point where it's almost ready to start thawing, but it doesn't take a lot of energy or oof to actually get out that scoop of ice cream. That's kind of what the discontinuous permafrost in the area where I'm from is like. And so it's very different conditions like that. And then as we move further south, it becomes more sporadic and isolated permafrost, where we're dealing with less than 50% permafrost or very isolated patches of permafrost from the old ice age. And so here's an example of a carbon. So this is a soil plug here that I dug up at one of our field sites. And you can see that this is a huge amount of carbon located in this plug. It's about, I don't know, foot down, but it's very old and very rich in carbon. So this is we had a VIP visit out here, and he had never been to the Arctic before, and he was like, I don't get it. There's nobody out here. Why should I care about this? And he just didn't get it, And so I finally took a shovel and I dug out this chunk of permafrost carbon. Is like, this is why you need to care about this. And he's like, okay, I got it. And, but it took a while, and it took a 2-hour drive out to the field site and talking to him and going back and forth with him before he really understood why it's important and why we care. So here's another plot about permafrost, showing permafrost and the changes in permafrost. So on the left is permafrost at different locations in Alaska. The bottom plots, the open squares, those are the northern continuous permafrost. And the top plot up there is the interior discontinuous permafrost. And what you see is that the continuous permafrost sites are warming up quite dramatically here and here. So these plots up here, so the bigger dots. But the discontinuous permafrost, they're pretty flatline, and that's because they're very close to the freeze thaw tipping point. And so all of these sites are at a 0.5 degree or 1 degree below the freezing point, and they're going through the phase change. And so any energy that's going into these soils right now are basically waiting for the switch to flip. And then once that happens, then the soils will warm up again, but then they won't be permafrost. They'll be non-permafrost. And so because the permafrost is so warm, it's that warm ice cream again. It doesn't take a lot of energy for these things to switch. It could be a footpath, it could be a wildfire, it could be a trail from a caribou that can cause a big switch in the landscape. So it's pretty. Yes, sir.
This material is heavily loaded with carbon dioxide. What's the source of that? It can't be photosynthesis. What is the source of this extra carbon dioxide?
It is photosynthesis. Right?
Well, it's underground. It can't see sunlight.
Well, it's like, so every year there's a little bit of growth of plant material from the sun. So we get 24 hours of sun or close to it. The plants grow, but because the soils are so cold and it's so cold in general, the bugs that decompose those soils or those things, they don't work fast enough to actually decompose it. And so you get a little bit, and so it builds and builds and builds and builds.
It's layered.
It layers. It's like a bank account that just doesn't get drained. Is that close to correct? Yeah, so that's why the soils are really old. That's why they store so much. That's where. So this is how we measure those points. This is from Vladimir Romanowski at the University of Alaska Fairbanks, and the right plot shows dead horse deep borehole. So the depth is on the left-hand axis. Going across the top is the temperature of the borehole at different depths. And so what's interesting about this is much deeper than the seasonal change that's felt every year. So every year, the sun comes out, the soils thaw a little bit. And so that little bit is called the active layer. And below that is permafrost. But that seasonal thaw every year, it only, it goes down maybe 1 meter, maybe 3 feet at the very, very most in this area. And so these measurements here are well beyond that annual influence of temperature. But what you see here is that from 1984 to 2015, that there's a shift going towards the warm, towards the right in these temperatures. And that's due to the only way it can happen is to a long-term climate signal that's propagated long-term over time, slowly warming up the soils. And so this was one of our first indications when I was a master's student, when we first started seeing this, is like, this is something new, this is something big. We need to be paying attention to this. Each of LAD's permafrost sites, they have a little net station that measures snow depth. They measure wind speed and air temperature. And then for the shallow wells, he has little hobo waters. And so you can see the little red blinking lights. So you can go down about 15 meters. And then once you get down below that, then you need to have this big spool and you just reel the spool down, take a measurement, record it in your field book, measure it, keep going down. So at incremental depths, they do that at a number of the sites. And then if we look underground, what's underground and what's part of our question one of the NGEE Arctic project is how does the landscape interact with the permafrost? And what drives a lot of the subsidence and things that go on underground are these ice wedges. And so the lighting here isn't super awesome, but here, these are massive things of ice that go down into the ground. They kind of go down pretty wide at the top. They come down and pinch out at the bottom, but they have irregular shapes at the bottom. Here's another big ice wedge here. And so this is in the permafrost tunnel just outside of Fairbanks, Alaska. And then it goes across the ceiling and over the top of you. So you can sort of like see these ice wedges. And these things take place during the wintertime. And so when it gets really cold really quickly, the soils become under tension and the ground cracks just a tiny bit. And during the spring snowmelt, that water runs into those tiny cracks and they tend to happen in the same place every year. And then it hits this ice at depth and then it refreezes. And when it refreezes, ice expands, right? Water expands when it's frozen and it builds out a little bit. Then the next year it will crack again, a little bit more water will go down, it'll crack and it'll build out and build out and build out. So these ice wedges take hundreds to thousands of years to develop. And if the lighting was a little bit better, you'd be able to see the striations. There's lines coming down here where you can see the cracks and where they fill up every year. It's really cool to see up close. And so those ice wedges, they're essentially pure ice. There's not much soil involved in those. And so you can imagine that if you took the ground and if it started to thaw, all that ice, becomes water. And so here's a small core from a borehole or from just a soil block full of ice. They just let it sit out. The ice melts, the sediment subsides or goes to the bottom, and the water rises to the top. And then you have a mess, right? If you have any kinds of structures. And so this permafrost and this permafrost degradation has a lot of different impacts on what goes on. So top left, permafrost has a big impact on berries and berry distribution. In a lot of the rural communities, those communities rely on the berries, seasonal berries for their subsistence and for their winter food supply. The center, this is just outside Fairbanks. This is a house. This is a very famous house that's fallen into the ground. And this was built prior to a lot of permafrost engineering and knowledge. This house was built directly on top of the ground on very warm permafrost. And so any heat from the basement caused the thawing of the soils and it just tipped over. And so all of my houses that I lived in, we built on stilts that went to bedrock or into something quite deep. And that allowed air circulation to go underneath the house, the cold air to keep the ground frozen. But this house was built long before that. The permafrost it degrades from the left to the right. So from very wet to very much drier. And that has big impacts on habitat, bird habitat. A lot of people care about that. In the bottom left here, it also has economic impact. And so here's two clippings from different papers, recent papers. The top one is Bethel. This is a small community southwest of Fairbanks. The permafrost is dying. Bethel sees increased shifting in roads. They used to have dirt roads. They got a bunch of money, they paved the roads, and that change in the energy balance with the dark caused a big thawing of roads. And so their roads became a big mess. And then a project that I worked on here is this Red Dog Mine, which is outside of Kotzebue in Western Alaska. And the permafrost there was falling apart. And the company, Red Dog Mine, had to build a big impoundment pond because the permafrost was thawing and the sediment load that was going down the stream was above the regulated amounts. And it wasn't their fault, but they had to prove that it wasn't their fault. So they ended up spending $20 million to build a big pond just to retain all their water until we got out there and say, hey, this isn't their fault. It's natural. The ground is just falling apart underneath them. And then on the right here, it also has a big impact on fisheries. Permafrost changes in terms of both the temperature. If you have a deeper permafrost, you end up with a deeper or warmer groundwater. And so that impacts the salmon. But also, we also have these retrogressive thaw slumps. So the center bottom. So we get a lot of sediment that pumps down into these streams, and that also impacts the salmon habitat. So our fisheries have been in trouble for quite a while now. And they think a large part of that is because of changing temperatures in the rivers, and which is directly or indirectly a permafrost issue. And then in this top right here, the change in going from a wetter environment to a drier environment. This is more of an NGEE question. You know, it also changes the energy and carbon fluxes and water distribution across the landscape. And so that's a question I've been thinking about for a while. You can see that the changes in permafrost also changes the ground surface. It changes how the water is distributed across the landscape. In the bottom there, you can see it's a little bit greener. That's where the water is flowing, where it used to be pretty uniform across there. This is in far north Canada, where it's really, really cold. And so they were very surprised to see this big change in rapid time. Societal impact. So this is again sort of the road issue. This happened right after snow melt, big sink. And this is becoming more and more common in where I lived in Fairbanks, where the snow melts, a bunch of water transports heat into the ground. You already have very warm permafrost and the ground just collapses basically. So it's not a surprise to go down the road and you see like a big sinkhole right next to the road, and you're like, oh, is that my car? It's going to be next. And then another interesting thing was right after I got up here, got down here to Tennessee, I received a phone call from a realtor, and he got my name off the internet, a permafrost expert, and he's like, I'm trying to sell this house. Half the house, the ground is falling off underneath it. It's like, I don't know how to repair it. And we've been getting quotes about it, and the amount of money that would take to build back and support this house would cost more than the house is worth itself. And he tried to get me to say, would you be willing to go to court or go to the insurance companies and say, this is an act of God because the insurance company is going to cover it? I said, no. It's like, I can't get there to look at it. And so it's a big problem. Here's another, this is by the university. Roads have to get repaired every year. They fall apart. The photo on the left here is the haul road. So going from Fairbanks to the North Slope of Alaska, there was a big flood. That water took out all those ice wedges. So these things here are those big ice wedges I was showing you that were underground. They eroded away with the water. And so the haul road, which supplies all the food, all the logistical support, all the supplies for the oil industry, was closed down for 3 weeks until they were able to build a new road. So it's a big problem. Okay, so the one on the right, so this is thermal erosion in drunken forest. Thermal erosion, I caused this for this was my PhD study site. And this is just me walking across the ground from, time after time after time over a number of years. Finally, there was enough of a path, the permafrost was warm enough, it finally started to go, and when it went, it went pretty quickly. Drunken forest, so when these ice wedges melt, the forest falls in on top of each other. And this is a problem in a lot of rural communities where people aren't able to access their traditional hunting or gathering grounds anymore. So a lot of times they'll be in these streams, the forest is falling on top of them, but they're not able to go upstream to get to their hunting grounds or to their fishing areas. And so they're saying that they're having to go out there and take chainsaws and chainsaw the way up the river, but that's just not feasible in terms of just time and energy and cost. So a few stories, a little bit of background. So that took a while. When I'm running out of time. And so I'll talk a little bit about my high latitude research and what I'm interested in. And as Ellen mentioned, all of my research revolves around exploring the magnitude, timing, and pathways of water in permafrost affected environments. So I'm interested in water, where it's at, where it moves to in these environments. And from the very beginning, I worked with a colleague of mine, and we did our postdocs together. She was an ecologist, I was a hydrologist, and we talked together and we decided, we just didn't communicate very well together. It took us a long time. But we have a pretty nice collaboration now, but basically everything is connected. And so you can't think about permafrost without thinking about the ecology. You can't think about the climate or the hydrology. You can't think about permafrost without thinking about ecology or hydrology or the climate. All these things interact, and you can't just be very siloed in your own study. And so some of the big projects I've been working on, far left is a boreal forest that I worked on with Jesse, very cool project. I've done a lot of work with snow shrub interactions. That's the middle slide there. And then the last one is this degrading permafrost and figuring out what causes the switch in permafrost from non-degraded to degraded permafrost. So because I'm getting close out of time, I'm just going to focus on the far right one. So this is Prudhoe Bay, far northern Alaska. You can see in 1990, almost no degradation. 2001, you start to see degradation. This is water falling into and in 2010, it continues. And so something happened between 1990 and 2001 that nobody really knows. It's still pretty cold. And we also know that permafrost degrades. It's degrading, but it doesn't degrade everywhere, and it doesn't degrade everywhere all the time. And so I've been interested in trying to understand what's the trigger, what causes the start of the degradation process. And once it goes pretty quickly, but trying to figure out how it goes is been a big question of mine. So we did a bunch of snow surveys on the Seward Peninsula. And so here we're showing 2 different years across our study site in 2017, 2018. In 2000, and then snow depth are the dots. And so the white, pink, and blue are pretty shallow. As we go into the light blues and greens and reds, those are much deeper. Snow is typically deeper in the shrubs, it traps it. But in 2017, pretty shallow snowpack, not much going on. 2018, pretty deep snowpack for what we were used to. In the summer prior to that, and summer after that, it was really warm temperatures, and the winter in between was quite warm. And so the 2018 year, our ground didn't refreeze all the way. And so this is showing one of those sites. And so 2016, 2017, these are different temperatures at different depths. So ground surface to 1.5 meters down. They have a warm temperature, warm summer. 2017, no snow. The ground freezes well below 0. It warms up quite warm the next year, 2017 summer. And then in 2017, 18, that winter, we had a lot of snow really early. And the ground didn't refreeze, and then it was really warm the next year. So what I think is happening there is that we have this really warm summer. It thaws the ground like it normally does. We have an early and deep snowpack. Snow is a really good insulator, sort of really nice insulator. And so with that early snowpack, that trapped all of the heat from the summer in the ground and prevented it from going out. This also followed up with a really, really warm wintertime, almost record warm winter. And then we had a really warm summer the following. And so this is all make-believe. And so what I think happened is that, I'll just go to here, is I think that the stars basically lined up where you have warm summer, you have really deep early snowpack, you have a really warm winter, and you follow it up by another warm summer. And then in that case, I think that might be, I'm calling it climate priming. And I think the climate primed the soils for degradation to take place. And so if all the stars line up, then something may happen in time and space. This could also work the opposite, where you could have really cool summers, you can have no snow, so all the heat escapes into the atmosphere. Have cold summer again, and you can basically harden the permafrost that might have been susceptible to thawing before. And so it could go either way. And so what we did is we took 1 by 1 square kilometers, and we started looking at the summer temperatures, precipitation, snow, and early and total snow. And we basically built this climate priming index. And so summer temperature, we use thawing degree days. And so as our proxy, and so thawing degree days is how much heat is added on to the summer during the thaw period. And so if you have a 1 degree above freezing one day, that's a value of 1. If it's 5 degrees below above freezing the next day, that's a value of 6. Over those 2 days, you've had 6 degrees of heating over that. And then the freezing degree days is just the opposite. If it's a little bit below, it's just the summation of how cold it is every day. And so by figuring out how warm or cold, that's our proxies. So this is 1905 climate priming. And so summer precipitation, early winter precipitation. So values is 0 to 500, and then the thawing degree days, the freezing degree days. And what we do is we do a cumulative probability distribution for each of these points for each of these components, and basically stack them up and add. So we have values from 0 to 1. So if we have a very, very warm summer, the warmest summer on record, that would have a value of 1. Have the coldest value, summer value, that'd be a value of 0. And so the maximum and minimum will be 0 and 6 for these things. And so in 1906, so this is Western Alaska. It ended up being pretty cold here. If we look at the same thing for 2017, 2018, so these are where we know it didn't freeze on the Seward Peninsula. You can see that we had a lot of summer precipitation in parts of the area. We had really early snowpack. The total winter snowpack wasn't that deep, but it fell early. And so it trapped that heat. It was very warm the summer prior. It was very warm during the winter, and it was very warm the following year. And we ended up with a big, much redder, much higher climate priming, which coincides with our what we observed on the ground. And so again, early when I showed the climate stripes, the sort of the candy cane looking thing, early in this century was a lot of blue, right? A lot of cold temperatures. We see that with our climate priming. And then again, more recently, 2018, 2019, we had back-to-back years where we saw our soil monitoring, soil temperature plots, they didn't refreeze. So that sort of coincides nicely. And this also coincides, these 2 years were also big years for the Red Dog mine. They had to build that pond. That's when they saw big flushings of sediment down into above their limits. And so they could tell that the ground was moving, and that also correlates with what we're seeing here. And so I'm running out of time. So what's next? So the NGEE Arctic project is gonna wind down in 3.5 years-ish. And we're starting to think about what's next, and I don't know what's next, but I think what would be really interesting is to move a little bit further south and you get into this very susceptible permafrost, very warm permafrost in the boreal forest. And the discontinuous permafrost, because you have very different, basically once permafrost thaws, everything switches. The vegetation switches, the water pathways switch, everything switches. And being able to model that currently, I don't think we're able to do that. It takes a pretty big investment in time and money and people power, for sure. So I'll wrap this up. So my, when I was in Alaska, a colleague of mine, Jesse, again, we started the Alaska Voices podcast. And this is our mission statement, builds bridges of knowledge by sharing conversations. And it was a way to get people to talk together and talk about different perspectives. And we share stories about the environment from community members as well as scientists. It was really successful. And so here's some pictures of the some of the voices. We in the top center there, we have elders. Far right bottom, we have elders. We have longtime friends. We have people living in villages talking with their colleagues. We have a policymaker. This is the head fire person in Alaska, wildfire manager with a fire scientist. We have mentor mentees. Yeah, family members talking together. And so it's been very successful. I was going to play a clip of Victor and Ryan. Victor lives in Lake, Alaska, which is way down here. And he talked a lot about just the changes that he's experienced over his lifetime, the stories that his family have been telling him. And I'm having problems with the audio. But if you wanted to stick around, it's about 10 minutes. I would be happy to put it on my speaker after we turn off the Zoom and the microphones and play it for you. So there's that. And then we've had really nice reactions to this. Well done in bringing science to the public. Incredibly moving episodes. Yeah, people stopped me in the stores and thanked me. And it was really, really cool project. And so with that, I'll finish my chat. I'm happy to answer questions, but I want to thank the Department of Energy and Dan Stover and Brian. Yes, sir.
What's your forecast for permafrost distribution over the next 100 years?
So the stuff that's north in northern Alaska, where it's continuous and deep, there will still be permafrost, but it will be probably a much deeper active layer. So the seasonal thaw, I would anticipate to be deeper than it is now. It's less than a meter now. I would expect it to be deeper than that. In interior Alaska, it's I expect it. I wouldn't be surprised if it started to leave the environment pretty rapidly. It's very warm, and the way the climate is changing currently. Once you flip from once you overcome the latent heat of ice, it takes a lot of energy to melt ice. And it would take a lot of energy to refreeze that same ice. And so given that the energy is going in the wrong direction, I would expect it to disappear from the interior of Alaska.
Well, I guess as you lose permafrost and then it dries out, you get usable stable land there.
Except for you still have permafrost underneath it. Eventually, yes. Eventually, yes. Short term, no. Short term, it's a mess.
Carbon dioxide and methane are both greenhouse gases.
Correct.
Which of those offers the biggest threat when you melt permafrost? I mean, they're both there in concentration, but which is worse in the long run?
With the it depends, right? It depends on if the landscape starts forming lakes, if the landscape becomes wetter, because if you have ponds or gullies and water fills in, then you'll release more methane. If the landscape becomes drier because water runs off, then the carbon dioxide will become dominant.
What's the source of methane?
The bugs and
Rotting material?
it's that big carbon plug, right? And a bit of water and bugs. Yes, sir.
In a successional stage, is there any hope that a successional stage of plants would proliferate fast enough to offset some of the release, or is a related question?
I don't know the answer to that question.
I was at the Bolton Research Conference 2 summers ago on climate engineering,
Mhm.
second one. So it's like 150 at the top atmosphere scientists on the planet. I've heard of the Gordon. And their consensus is that the tipping point might be as close as a decade. Tipping point meaning
To what?
after that,
Yeah,
we're done. I mean,
well,
we can't stop it. Like even if we cease, like you said, with the activation energy with ice,
mhm.
it requires momentum.
Yeah. Yeah, I don't know the dates of that. I know that my former boss has talked a lot about if the natural environment gets to the point where permafrost is thawing without anything that we do, if we shut off everything currently, we're getting rapidly close to the natural environment taking off anyway. I don't know the date of that, but that's something he's talked about and is concerned about.
Seems like it'd be safe to say the tipping point for permafrost may already have passed.
Depends on where you're at.
Okay.
Depends on where you're at. It's close in some places, right? But it's not.
The sediment you talk about in the water, that comes from erosion, how does that kill the salmon?
It affects their spawning grounds. They require very specific conditions in terms of water temperature, in terms of the quality of the water, and the sediment impacts that.
Do you assume that things are progressing the same way over in Siberia? Presumably the permafrost in Siberia is following along the same pathway?
I don't know the answer directly, but I would suspect so. There's a lot of big fires going on there. They have very different vegetation over there. I don't know, but I would expect the permafrost to be warming for sure. Yes, sir.
I have a number to share with you.
Okay.
Current atmospheric concentration is 400 parts per million. Permafrost releases its inventory times 2.5. That's plus 1,000 parts per million. Put 1,000 parts per million of carbon dioxide in perspective. A mature southeastern rainforest, like where we live, has a carbon loading of 1 gram per square centimeter. That's about the richest forest you can possibly get. 1,000 parts per million is by definition 1 gram per square centimeter. So it's like that's equivalent to a mature rainforest over the entire planet Earth, land and ocean included. That's how much gas you're looking at.
That's potential. I would push back. It's not all going to be released at the same time. And it's going to take some time. And so it's not going to be the bomb that everybody, I don't believe it's going to be the bomb that everybody talks about.
Alan, do we have questions on the Zoom?
I see no question
Okay.
on the Zoom.
All right. Well, thank you.